that occurs at a certain point. And why that's significant? Well, if we look here at 20 millimeters, for this particular case, if we have 20 millimeters of this insulation, and you put it on the system, the resistance, the total resistance will be the same as if we had no insulation at all. So because of that, we know that in order to get any value out of putting insulating material around this pipe, the insulating material needs to be thicker than 20 millimeters. It needs to be thicker than 20 millimeters. So, like I said, there's convection and conduction that are competing here. And there's this critical thickness. And the critical thickness is this minimum that defines where, after that point, the total resistance does nothing but increase. Well, that critical radius or thickness is the ratio of the thermal conductivity of the material to the heat transfer coefficient on the surfaces of the material. So that concludes our look into 1D steady-state conduction with no internal generation. And this is a plot from your book. This is table 3.3 that explains or presents concisely the heat equation, the temperature distribution, the heat flux, the heat rate, and the thermal resistance for the case of a plane wall, of a cylindrical pipe or wall, and a spherical pipe, or not a pipe, but a spherical system or a wall. So this is something that's useful to refer to for solving problems. And we talked about what the critical radius of insulation is for the cylindrical system, that is K over H. Well, you have a similar thing for the sphere, and it's 2K over H in that situation. So we didn't go through the spherical wall derivations, but I encourage you to look in your book at these, and it's very similar to the cylindrical wall. And then we'll have some homework examples that we'll work through to help us better understand that. Changing pace. All right, so now we're going to deal with 1D steady-state conduction with energy generation. So it's going to complicate the problem just a little bit. And energy generation, of course, by now we're familiar with it. Q dot, or Q triple prime, is watts per meter cubed. So this is volumetric energy generation. And there are many examples of this in your life, in the real world. One is nuclear generation. So we have our Springfield nuclear power plant. And basically, when you have a nuclear reaction occurring, that it's generating energy in the entire body or system, and that's a form of volumetric thermal energy generation. Solar absorption is also an example of volumetric energy generation. So you have a solar absorber. The light not only hits the surface, but it penetrates into a material and is absorbed throughout the entire material. This can be an example of uniform or non-uniform thermal energy generation, but most likely it's going to be non-uniform because of the directional dependence of that solar flux. But it's an example. So with thermal energy generation in material, it can be uniform or it can be non-uniform, just like it likely is in the case of a solar absorber. The Earth, the ground beneath you right now, the Earth generates a lot of thermal energy. And it can be modeled as a system, as a spherical system, that has internal generation at its core. So let's look at the system in a simplistic form, the 1D plane wall system. So the question here is energy being added through generation to the system or being subtracted? If you look at the temperature profile, well, in this case, it's being added because you can see here that the temperature goes up and it has a maximum near the center of this wall that's higher than the fixed temperatures and the boundaries on both sides. So the governing equation, the heat equation, simplifies to this form in this case, where we just have one-dimensional steady-state heat conduction with generation, a plane wall, so it's Cartesian coordinates. And the general solution for this, the temperature profile, is parabolic in shape. So that makes sense because we just saw what the temperature profile looks like. And we would expect mathematically for it to have an x squared or a parabolic term. But that means something even more significant. Think about Fourier's law. So we take this temperature profile and we take the derivative of it with respect to x. In the linear case, x goes away. So that heat rate is independent of x. But in this case where we have a parabolic temperature profile, we end up with a heat flux and a heat rate that depend on x. So it's here heat flux, function of x, but it's also the heat rate is a function of x as well. So the big conclusion is when you have this generation, you have this parabolic profile, that you cannot apply the circuit analysis that we worked on for the past couple lectures. So we have to do something else. All right, so we have a wall here again. And the question is, what is the form of the temperature distribution for the case where there's no generation, when the generation is minus, so energy is being extracted from the system, and for when the generation is positive, energy is being input into the system? Well, we already answered that question for one of them. But we determined that for this case, because the temperature is higher here than it is at the two sides, that energy is being put into that system. So if energy were being extracted from the system, then we would probably mirror this line, this curve. We would mirror it about a line so that the parabola would now be in the other direction. So it would be shaped like a bowl. And if there was no energy generation at all, then the line would be linear between T1 and T2. So how does the temperature distribution change as Q prime, or the heat generation, increases? Well, in this case, if we have the boundaries fixed, then the temperature is going to be the same at these boundaries. But if we're putting more energy into this wall uniformly, then we should know, or we should have a good feel that this curve or this parabola will start to become steeper. So instead of being wide, it's going to collapse, and the center point or the maximum point will increase over what it is at a lower Q dot.